Alright, so for homework, you should have gone onto the Learning Hub and either watch the video or take a look at the PowerPoint over the guided notes that you were given on waves. Okay, the video would have gone through and explained everything that was in the packet, but I want to go over a couple of things again today because they're going to be a little bit relevant to what we're doing, or they're just a little bit harder to understand, so I want to give you a couple ways to take a look at it. So the first of them is called superposition. Superposition is a thing in physics that actually shows up in a lot of different places. Basically, it means that if you have one thing and you have another thing and you add those together, they make a new thing, right? That's what actually superposition is. Forces do the same thing. If you have two different forces on one object, then they basically behave like a third force. That's the addition of the two of them together. When it comes to waves, let's say we have a wave that looks like this, which is traveling this way, and we have another wave that looks like this that's traveling this way. When they meet, they end up making a wave that looks like this. So it's twice as big, and actually the way I've drawn it, it's not really twice as big, so it's twice as big, but the same width, because the width doesn't add, it's the amplitude. It's the highest part of the waves that add together. So this is what we call constructive interference. Constructive interference. Okay. You can have destructive interference, and that would look like this, where you have a wave that's like this and a wave that's like this, and they're going to be going towards each other again, in which case, if they have the exact same height, then when they add together, you would just end up with a flat line. And make that a better flat line. There we go. And that's just because when you have, let's say, a positive, this is a distance here, it's an amplitude. If you have 2 centimeters here, and you had a negative 2 centimeters here, it's negative because it's below the axis. When you add that together, you get 0. So they destructively interfere. But they're waves, they pass through each other, and so sometime later, this one will be over here, and then this one will be over here, so still moving in the same directions that they were. It's just when they happen to be on top of each other, they add together in this thing called superposition. So to show you this in kind of real-world scenarios, I'm going to show you a video that involves a slinky, showing you how they add together, and it's kind of cool. It has a little bit of slow motion there, so you can really see what's going on. So take a look at this video. So from the video, you can see that they have some markers that are set up along the slinky. So there's a marker here, there's a marker here, marker here, here, and here. So just to really explain what's going on, right? If they send a wave that's this high and a wave that's this high, neither one of those waves are big enough to knock down the markers that are right there. But when they add together, so let me put that in a different color. So when they add together, now they're high enough that they can knock down the marker that you see there. So that's with constructive interference then. And if we were talking about destructive interference, let me get these out of here. So destructive interference, if they were to have sent a wave, let's do this in a different color, that was this high, and a wave that was this high, make that a little bit better, then that means both of these markers will be knocked down, but when they get to the center point, they should add together to give you this, nothing, so neither one of these markers will actually drop or be knocked down. So that's destructive interference. So that's what we call superposition. We also call it wave interference, so it's all the same kind of thing. So the next thing that we have is about how that wave interference works for sound. So for sound, we have different frequencies, right? We have different pitches, different notes that get played. So if you have a wave that looks like this, okay, so it has a pretty set frequency and amplitude, Then you have a secondary wave that is just slightly off from that. Then we have things that start to happen. So I'm going to show in green some areas here. So in this area, we have a place where the two crests of the two waves will add together. So it's like a constructive interference right there. Okay. Here we have the two troughs of a wave adding together. So we have another constructive interference. But right here in the middle, right, we have a trough and a crest that's adding together. So if this new wave, that is the addition of both of these together, will start to look like this, where it's really big, but then gets really small, and then gets really big again, and then gets really small, and I'm a little bit off, but that's okay, you get the idea. So it gets really big again, and then gets really small again. So if we're talking about sound here, the bigness of the wave, I know that's not a word, the bigness, the size of the wave, that's talking about the volume, right? So amplitude of the wave equals volume. So if you have a big amplitude, you have a big sound. So if this is a new wave that we're talking about, then the amplitude is talking about how loud it is. So it's going to get really loud and then really soft, and then really loud and really soft. So the LabQuest can actually do this. So take a look at this new video that shows how a LabQuest is playing two different sounds that are very close to each other. All right, so this is a LabQuest, and we're going to play around with some audio generator functions here. So I'm going to play a sound for you. All right, so that's concert A, 440, right, 440 hertz. Okay, now I'm going to play a different sound for you. This is just slightly off concert A, 441. All right, can you tell the difference? Are they two different tones? They don't really sound like it. But what if I play both of them together? Do you hear that oscillation in the loudness of the sound? It goes up and down and up and down. It gets louder and softer, louder and softer. So that's what beats are when it comes to sound. Alright, so hopefully you could hear it. Maybe the volume of the speakers need to be turned up a little bit, but hopefully you heard that when this one was 440 and this one was 441, when we're talking hertz, that's the frequency. That's the how often it oscillates up and down. Then we get this this wavering in the amplitude, right? It doesn't really sound different when you listen to them individually, but you get a wavering in the amplitude, and so the sound gets louder and softer and louder and softer. So that it turns out that the frequency of that oscillation in the amplitude, so getting back from a really big amplitude, I'm going to do this in a different color, so a really loud sound here to another really loud sound here to another really loud sound over here, this has a frequency of 1 hertz. Right, 1 hertz. So it happens once every second. You can kind of go back to that other video and think about wow, wow, wow. It's 1 every second. So it turns out that we call this beats. Beats. And the beat frequency is something that we like to talk about. So the beat frequency is just equal to the two frequencies subtracting, and it's an absolute value, so it doesn't matter which one's first. So if this is 441 and 440, and we subtract them, we get 1 hertz. If we had two frequencies that were like 950 and 945, then the beat frequency would just be 5. All right. So that's beat frequency. The last thing that we're going to go back over just before we get into the lab today is this thing called Doppler Effect. So Doppler Effect is something a little hard to explain using static images, which is what I can do here. So I'm going to show you a couple of videos here, the Doppler Effect. But basically, when you have an object that's making a noise and it's moving towards you, you end up hearing the sound a little bit different than when it's moving away from you. And you all have experienced this. If you've ever been in a car and someone with a siren happens to drive by, or a motorcycle goes by and you can hear the really loud whine of the engine of the motorcycle, you kind of hear something like this, and like, right? So it starts off with a high frequency and then it drops to a low frequency. And it's all about how that's moving towards you or away from you. If you were on the motorcycle, or if you were in the siren, or in the thing that's making the siren, you wouldn't hear any difference in that pitch. So what's going on here? So I'm going to play a couple of videos here to show you what's going on.
Fun science, fun science, fun science, it's a science of fun, yeah. Today I'd like to tell you some cool things about light! Now, as I'm sure you're aware, the speed of light is 299,792,458 meters per second, which is pretty bloomin' fast. To give you an idea as to how fast that actually is, it would take a beam of light 1.255 seconds to travel from the Earth to the Moon. The speed of sound is only 340 meters per second, which is still pretty fast, even though, thanks to science, humans have managed to go faster than that. But if you want to go faster than light, then sorry, you can't. It's not possible. It's theoretically possible that we could one day travel very, very nearly almost as fast as light, but to go faster than that, no, sorry. Now, before I can tell you about all of the really cool stuff that comes with light and the speed of light, I have to tell you about this other thing called the Doppler Effect, which is still really interesting, so, don't leave just yet. The Doppler Effect is the change that you notice in the frequency of a wave when the source of that wave is moving relative to you. For example, imagine that you're sitting by a canal enjoying the lovely British weather when suddenly I appear next to you screaming like a lunatic. From your perspective, it's just really, really weird. However, if theoretically I wasn't standing next to you but was running past you at 80 miles an hour, still screaming just as I was before, as I approach you, the pitch of my scream would be higher, and then as I pass and run away from you, the pitch of my scream would drop, even though from my perspective, I'm screaming at exactly the same pitch as I was when I was standing still. The reason this shift in pitch happens is because when I'm sitting still and screaming, the sound waves are emitting from my mouth uniformly. But when I start moving, the sound waves in front of me get squished up and the sound waves behind me get stretched out. And it's this change in the frequency that causes the change in pitch as I pass, and that is what the Doppler effect is. The reason the Doppler effect is important is because it doesn't just apply to sound, but it also applies to light. Bet you didn't see that one coming, because it's not a video about light or anything like that, is it? Oh. So just as when something is moving and emitting sound, you can hear a difference in the pitch of that sound, when something is moving and emitting or reflecting light, you can see a difference in the colour of that light. For example, imagine that we're in exactly the same running canal situation as before, except this time I'm not screaming like a lunatic, and instead of running at 80 miles an hour, I'm running at very, very nearly almost the speed of light. What would you see? Well, you probably wouldn't see anything at all, because as you'll remember, the speed of light is very, very, very fast, and I'd be gone before you even knew I was there. But let's pretend that you had a magic iPhone app that would let you take pictures of me travelling very nearly at the speed of light. What would you see? Well, when I'm running towards you, the light in front of me gets squished, and the frequency of that light gets shifted to the blue end of the visible light spectrum, and so I appear blue. And then as you see me running away from you, the same thing happens in reverse. The light behind me gets stretched out, shifts to the red end of the spectrum, and then I appear to be slightly red. Now, this change in the frequency of light is something that happens all the time. In fact, it's happening right now as I move forwards and backwards from you, but the change is so negligible that you can't notice it unless something is travelling at very, very nearly the speed of light. But easily the coolest thing that happens when you travel at very, very nearly almost the speed of light is that when you do, time slows down. All clocks, whether man-made or biological like me, tick slower when you're travelling that fast. So back to our thought experiment where I have the ability to run very nearly at the speed of light. Imagine that I decided to take a couple of minute tour around London travelling that fast. Well, it might have only seemed like a couple of minutes to me, but to you, travelling at normal human speed, it would have been many, many years. And so by the time I returned from my very short run, you would have died of old age. And that, ladies and gentlemen, is light. This is the end. Bye.
You've just had the almost imponderable joy of watching Charlie Is So Cool Like, which makes you like cool.
So from the video, you learned that it's all about how the thing that's listening to the wave is interacting with the wave itself. So if you're hearing waves that are really close to each other, then you're going to hear a frequency that's high. If you are listening on the back end where those waves are really far from each other, then you hear a frequency that is low. And it's not about that the frequency of the object is changing, it's changing relative to how it's moving towards you. or away from you. So that's called the Doppler effect. So what happens though if the thing that is moving begins to outrun the waves that it's creating? So we have this thing called the sound barrier, and the speed of sound, the velocity of sound, is somewhere around 343 meters per second. That changes actually depending on the air temperature, but we can say on average it's about 343. So if you start moving faster than the speed of sound, so maybe you're in a jet plane, you're moving faster than the speed of sound, then all of this waves that you're creating would be behind you, because as soon as you create them, now you're in front of them. So when this happens, this is called a sonic boom. It's called a sonic boom. That's when you break through the sound barrier. It's basically all the waves that were in front of you, you crashed through them, and it lets out a whole lot of energy. So take a look at this new video. It's about a person who can crack a whip really, really well, and they use some pretty interesting technology to see the sonic boom that a whip crack actually makes. Because if you didn't know, a whip crack actually breaks the sound barrier. So take a look at this video.
In case you're just joining us or haven't been paying attention, maybe a quick recap will whip you into shape.
Oops. There we go.
He said oops.
Our time warp high-speed cameras are able to capture all this bullwhip action like you've never seen before. Almost all the action. See, a whip breaks the sound barrier. That crack you hear is actually a sonic boom.
I haven't actually seen like the sonic boom itself, like the waves coming off.
Could it actually be possible to see what a sonic boom looks like? We know where to go to find out. Jim Bales at MIT's Edgerton Center works with a little-known photographic setup called a Schlieren. The Schlieren can actually capture light when it's distorted by air, which is exactly what a sonic boom does. To do this, the intricate setup must bounce light off mirrors and into our high-speed camera.
Push in a little bit. There you go.
Adam's target will be a lit candle. The trick will be to blow it out with a single crack of his whip. If done right, the Schlieren camera should show us the whip's sonic boom.
All we gotta do is have you get right at the target, and we'll be able to see everything.
All right. We're queued up, Matt, so go ahead and crank it.
I'm ready.
Let's see how the expert fares under pressure.
Nice, you got it.
Let's see this
What does
one.
that look like?
This guy doesn't even flinch, but everyone else does.
And he's got the aim.
Oh, liar. Look at that.
Then, the moment we've been waiting for.
Right there, you can see the moment it breaks the sound barrier as you come through.
Not only is it twisting, but you can see each individual tassel create its own little wave. So I'm seeing almost 10 waves through there.
Look again. What we are seeing is distortion caused by the sound barrier breaking. This wave can be heard as a crack or a boom, and the difficulty of penetrating this barrier, seen here in microcosm, is what made Chuck Yeager's, remember him, accomplishment so amazing.
That was really slick. I didn't think I'd ever see anything quite like that in the Schlieren system.
All it takes is a whip with the right aim and about 30 seconds of time, and we're set.
So let's recap. We took a guy who can destroy things
There it is.
and throw fireballs with a bullwhip. And we confirmed he also breaks the sound barrier daily.
There it is.
You know, he might have a future in Hollywood if he decides to lose the hat.
All right, so a sonic boom is pretty cool when you break through the sound barrier. So they were looking at how it was affecting the air around it, and they were looking at how light was bending through the air, and that's how they visualized that sonic boom from the whip crack. So it's pretty cool. All right, so we're going to get into looking at the lab. All right, so the lab, it looks like this. So all of your lab stations have one of these things on them. So you have a stand, right? And so you have this lovely thing on top and a lovely thing on bottom. and there's a elastic cord that is going between the top and the bottom. All right, so elastic cord. So there's a couple things that are also hooked up, or you have available that you're going to need to hook up. So one of them, you should recognize this. This is the timer that we've normally hooked up to photo gates. This time we're not going to hook it up to a photo gate. So, but you do need a timer, and you need to get out at least one of the cords. Let me start over. One of the cords that has one of the phone jack things on it. So you're going to need one of those. And this is what's in the other box. Okay, the other box. So it's the sound and motion box. So what happens is you will need to hook everything up. So this is a thing that needs to go to power, so that's going to be hooked in. You'll hook the phone cord thing all the way into the place where you can hook it up into the sound and motion thing. And then we need one of the, looks like an aux cord is going to come around and hook up to the bottom of the thing that's on the physics stand. Okay, so once you get all that hooked up, you'll be good to go. And all this is kind of explained in the lab. I'm not sure if the hookup is explained in the lab, so that's why I'm including pictures here. So all that is there. What's going to happen is that you are going to start shaking the string right here. You're going to shake it, and by shaking it, you're really looking at the frequency at which you're shaking it, which you'll control with this right here. Okay, you'll control it with the frequency right here. You'll need to push this button. You'll actually push and hold it down until the light is on the very, very bottom, where you're talking about waves. Okay. This has got no screen on it, so this is what this is for. So this is going to tell us the frequency, which means that you need to push this button until it reads the frequency of it. In the lab, you're going to be measuring frequency for when certain things happen. So take a look at this video about what happens when you get to a just the right frequency for something to happen. So hopefully what you saw in the video was that when you get it shaking at just the right frequency, you end up creating these patterns that show up on the wave or on the string. Okay, and so it's going back and forth, back and forth, back and forth, back and forth, but you can basically see this pattern right here. And this is what's known as a standing wave. So one of the first ones I showed you was this pattern, and then there's one that has, well, let's see. That's close enough. So you saw 4. Okay, you saw 4. So in the lab, you're looking at what frequencies cause these patterns. Okay, what frequencies cause these patterns? And so this would be having 4. The other one would be having 2. My suggestion to you is when you get into the lab, try to find a frequency of some of the mid-range ones, like 4 or 5, and then work your way up and down from that. And then you take your data. So at this time, the substitute will hand out the lab to you, and you'll have about 25 to 30 minutes or so, depending on how quickly you guys work, to get through your data. So I would suggest taking all the data that you can before trying to do any kind of the analysis questions. Yeah, we'll come back and take a few notes. So if you could pause the video right now and do the lab, then we'll resume the video when you guys get back. All right, welcome back. So this is the notes that you have. So if you haven't already gotten the notes, please have the substitute pass the notes out to you. So these notes are called the Standing Waves Part 1. This is the physics of music. So if you're into music, specifically stringed instruments at the moment, then hopefully you'll find a lot of really cool stuff in today's notes. So this is Standing Waves, Physics of Music. So sources of sound. So vibrating strings will have sound. Vibrating membranes like drums, air columns like a flute, oboe, organ, vibrating steel bars like a xylophone. Most instruments involve more than one vibrating body. So like a vibrating string on a guitar or piano also has to do with the body and the shape and the air cavity that's on the inside. All has to do with how the sound comes out. So we know that everything that creates sound has some kind of vibration that goes along with it. All right, so vibrations mean sound. So strings. When we produce a standing wave, they can take on lots of different forms, and so we saw lots of forms in the lab. And these are the first 6 forms that we have for a standing wave. These are called harmonics. So this is known as the fundamental harmonic or the first harmonic, and then you have the second harmonic and third harmonic. So while we're kind of talking about this, you can be drawing these diagrams on your notes. Now with the production of standing waves, so how do we produce standing waves like this? And why are they called standing waves? Well, you saw in the lab that the wave patterns, basically when they form, they look like they don't move anymore in terms of a wave going up versus a wave going down or forward or backward. It doesn't look like the wave's actually traveling down the string anymore. But it turns out that it is. So if you end up with a string where one side is constantly going up and down, then you're going to produce waves and waves and waves and waves. But when it gets to here, the other side, that's going to hit and it's going to reflect back, and so you end up with waves going back. So when the waves that are going back interfere with the waves that are going forward, then you can end up with a pattern that is a standing wave. And it turns out that only happens for very specific frequencies. So take a look at this video, which kind of shows the production of a standing wave on a really big slinky.
Standing waves are a result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode. Sending the pulse at twice the frequency results in the second harmonic. If I triple the frequency, I get the third harmonic.
All right, so you saw from the video that these waves are produced when you have waves that are going out versus reflected waves that are coming in that interfere with each other, and they only happen at very specific frequencies. And there's actually a relationship between those frequencies as well, where if the fundamental happened to be, say, at 10 hertz, then the next one would be at 20 hertz and 30 hertz and 40 hertz and 50 hertz and 60 hertz. So there's a relationship. There's always an integer multiple of the fundamental. We could do it differently. What if the first harmonic happened at 15? Then the second harmonic would happen at 30, and then it would be at 45, and then it would be at 60, and it would just keep on going in that same pattern. Okay, it's always the integer multiple of the fundamental. Well, what are we talking about fundamental? These things are called harmonics. So the fundamental harmonic is the first harmonic, the first standing wave that you can make on a string. Okay, so then the second one would be this guy right here, where it's coming back and it flips over like that. Okay. Then the third harmonic has 3 of those little loops on there. 4 of those little loops would be the fourth harmonic, and you just keep on going on. Hopefully you saw the relationship in your lab about how it increases with the frequency in that same pattern, or at least roughly that same pattern. So we're talking about frequency going up, right? Frequency goes up as we get further down in our harmonic. What happens to our wavelength? Well, a wavelength is 2 of these little loops that you can see. They're called antinodes, right? So we have this right here. That's one wavelength. So how much of the string is creating one wavelength? Well, you can see we actually have 3 different wavelengths here. So if we call the length of the string L, then L would be equal to 3 wavelengths, or that a wavelength would be equal to 1/3 of L. We can do the same thing over here, right? Let me do that better. We have 2 different wavelengths on this one, so that means a wavelength would be equal to 1/2 of L. What about if we were in the middle of these 2, right? So how much of L is created here? Well, we have 1 wavelength, we have 2 wavelengths, we have 2.5 wavelengths. So we would write that as our wavelength, which is our Greek letter lambda, right? So our wavelength is equal to 2/5 times L. Okay, but that doesn't really kind of fit with our pattern here. So what if we change these guys? Instead of it being to 1/2 and 1/3, what if we changed it to lambda is equal to 2 fourths L, and what if this one was lambda was equal to 2 sixths L? Well, can you see the pattern yet? This would be 2 thirds L. This lambda would just be 2 halves L, or just all of the length, which that kind of makes sense. We have one wavelength right here and here. So that means this has to be 1/2 L. So our equation then would be that the wavelength is equal to n over 2L, where n is the harmonic number, which harmonic you're looking for. So if it's and I got that wrong. I got it wrong. So it's I see what I did. All right, so this guy right here, it would not be 1/2 L. It would be 2 over 1 L. There we go. There we go. So we have to have two of our lengths of strings in order to even get a full wavelength here. So you can see there's always a 2 on top, and then there's a different number on bottom. So it'd be 2L divided by the n, which is the harmonic number. There we go. That makes a little bit more sense. So that's our wavelength. And this is our frequency. So how do wavelength and frequency relate to each other? Well, you might remember that we have this thing called the wave equation, and you hopefully would have gotten this before this physics class, but you might not have. The speed of any kind of wave is equal to the frequency multiplied by the wavelength. So in this case then, that means our frequency multiplied by the wavelength can be like this. Frequency is equal to f, and then it'd be multiplied by 2L over n. And that would handle all standing waves for an equation. So another way that we could write this actually is that the frequency is equal to 2L over n, V. And that's actually what we're going to use for our sample problem. So what is the frequency of the first three harmonics? So the frequency is going to be this 2L over NV formula. So L is 1.2 meters. Our V is 720 meters per second. So we would have 2 times 1.2 meters divided by, let's do the first harmonic first. So 1 multiplied by 720 meters per second. So this would be 2.4 divided by 720. And I'm going to have to apologize. This is what happens when you make these videos when you're tired. So let's go back for a second. If velocity is equal to F2L over n, right? I think I just did my algebra wrong. So if velocity is equal to F2L over n, then what is velocity equal to? Or what is frequency equal to? Sorry, so frequency is equal to NV over 2L. So there we go. That makes a little bit more sense to me. So NV over 2L. So I just had it backwards. I did my algebra wrong, and I apologize for that. So if our first harmonic then would be 1 multiplied by 720 divided by 2 times 1.2. And that would be, let me get my calculator out, so it'd be 720 divided by 2.4 gives us 300 hertz. All right, 300 hertz. So if the fundamental is 300 hertz, what does that mean the second harmonic is? Well, if we the only thing that would change up here would be a 2 that would be plugged in right there. So all it would do is just be the fundamental multiplied by 2, so it becomes 600. What about the next one? Well, that'd be 900. And those would be the first 3 harmonic frequencies. We got on the previous one that the wavelength is equal to what? I'm going to make sure I get this one right. 2L over n. So 2L over n. So if we wanted to do the first, so the wavelength would be equal to 2 multiplied by 1.2 divided by 1. So that would just be 2.4 meters. Okay, what would be the next one? Well, it would be 2 times 1.2 divided by 2. So that just give me 1.2 meters, so it's half. And then what about the next one? Well, it would be 2 times 1.2 divided by 3. And I don't know that off the top of my head because I'm too tired. So that gives me 0.8 meters. All right, so part C, what is the wavelength of the sound wave the first harmonic produces? So this is getting out of the string vibration and into the frequency of the sound wave. So what is different about that? Well, the sound has 343 meters per second as its speed, so 343 meters per second. So we want to know what the wavelength is if the frequency is 300. So that's going to be V is equal to frequency times the wavelength, and the wavelength would then be the velocity divided by the frequency, or 343 divided by 300. So 343 hertz divided by 300 meters per second, and that will be obviously something a little bit bigger than 1, so 343 divided by 300 gives us 1.14 meters of a wavelength. All right, so hopefully this helps out with your homework. So we're going to get a number of things after this video is done that'll be considered homework. You'll get some practice problems. You will get some a ranking task, a couple of ranking tasks, and I believe you'll get a free response question. No, I think that's maybe next time. So some practice problems, some ranking tasks, and some free, so practice problems and ranking tasks. Cool. All right.